Hi, so we're going to start talking about hash tables, and in this video, we're going to touch up on some of the basics. Let's start by doing a very quick review of some of the abstract data type that we've studied previously. So we've studied linked list, and um, we also studied binary search trees. And if you remember linked list, for the insert operation, if we just insert it to the head, that's O of 1. But if it's an order linked list, then it can potentially be O of n. And for remove as well as the find operation, they're both n because typically we'll have to search through the list. Half of the list on average, but worst case, the entire list to find something. For the BST, most operations is log of n, which is vastly better than O of n, but still it takes time, right? So in the real world, um, in some applications or many applications, we actually really want an O of 1 operation or a constant time operation. And typically that operation is the find operation because that's what we use most frequently. So we actually do know a O of 1 data structure, at least for find. And can you remember what that is? So that is array in most other languages. It does not exist in Python. So in Python, it's list. That is kind of operates like array in the other languages, but it also has some characteristics of a linked list. But anyway, array or list, if we know the index of the item we're looking for, then we can retrieve it in O of 1. Constant time, right? So for a very simple example, if we have 10 students and if we only have, the student IDs is only from 0 to 9, then, and we have an array that has 10 slots, then we can put each of the students at the position that is indexed by their ID, right? So the first student with an ID 0, we can put it at index 0, second student with ID 1, and we can put it in slot index 1, so on and so forth. So that is, and if we want to look it up, if we want student ID 5, we can just go to the slot in the array at index 5, and we can retrieve that student in constant time. Now, however, in the real world, it really doesn't work like that, right? I mean, we have way more than 10 students, but more importantly, the IDs are often a lot bigger, right? So at Foothill College, the CWID, they're 8 digits, so that's 100 million values. So if we want to use the CWIDs as an index into an array, then the array has to have 100 million slots. That's a very, very big array. Um, and even assuming we have that much space, another problem is typically the college only has around I think around 20,000 student plus staff. So and if we allocate an array that can hold 100 million students, we are wasting a lot of spaces. Another problem is we don't always look up by CWID, right? Sometimes we want to look up by your last name, your first name, or something else. So if we want to look up by name, that's a string, right? And we cannot use a string as an index into an array or a list because, well, that requires an integer. So what we need is some function that can actually transform an arbitrary key. So the arbitrary key can be the ID, can be the name, or something else. We want to be able to transform the arbitrary key into an index so that we can use it to look up the data in our list or arrays. So this type of function is called hash functions. And then a hash table is just a data structure that utilizes a hash function to figure out where to insert, remove, and find things in an array. So just as an illustration of how hash function works, So let's say, we have CWID, these CWIDs, kind of random big giant numbers. We feed them through hash functions. Hash function, each single one of them, feed them through a hash function. So maybe this number, whatever the hash function does, it transforms it into the number 0. And then we can look at slot number 0 at index 0 and find the student with that CWID. Another hash function, my output value of 2. And then we looked at slot 2 to find that student with that CWID. Okay. There is there's a little comment here. There's a simple but crucial step that is missing from this picture. We'll get to that in a bit. And okay, now as you can kind of imagine, if we hash, a giant number into a smaller number, then it can potentially happen that two giant numbers can end up being hashed to the same small number. Okay, so that means like there can be potentially two students that we want to put that will end up in the same place. So this is called a collision. It will happen, and it somehow must be resolved. And we will talk about collision resolution later. All right, and finally, just a terminology. I mean, I keep calling these slots, array elements, or whatever. There's a very particular terminology for these things in hash table. They're typically called buckets, and that is because, as we just saw, each bucket can potentially store multiple items. So anyway, each one of these can be buckets. It might not be used, or it might store one item or multiple items. And then there is another very important number in hash table that is called the load factor. So, and it's a function of two other numbers. One is what we just saw, the number of items, right? So in this case, it's the number of students we're going to store it in this hash table. And then the other number is the number of buckets, right? How many buckets there are in the entire hash table. The ratio, the number of items over the number of buckets, is called the load factor, or sometimes we call it lambda. Okay, so kind of think about what lambda mean. What does a large lambda mean? A large lambda, let's say a lambda that is bigger than 1, or let's say 10. What that means there are 10 times the number of items compared to the number of buckets. So each bucket is going to have to hold 10 items. So that means there are lots of collisions. Okay, and where there are lots of collisions, there are probably, as you can imagine, problems. Okay, but if a small lambda, let's say a small lambda that's less than 1, that would mean that we have many more, or more number of buckets than number of items. And if the lambda is very small, it may mean we're wasting a lot of spaces. Okay. Anyway, so load factor is very important for performance. Sometimes, depending on how we resolve the collisions, it's even necessary. A certain value of load factor is necessary for correctness. So we'll look more closely at it when we talk about the details. Okay, lastly, this slide really doesn't quite belong here, but I don't know where else to put it, is, well, hash tables are hugely important. As a matter of fact, two very important data structures, built-in data structure in Python, set and dictionary, they're both implemented as hash tables and using what's called quadratic probing conflict resolutions. I have a link to that here that actually kind of details the implementation. It probably doesn't make a whole lot of sense right now, but once we finish studying the hash table, I think it will be very interesting to come back and read these details here and actually the Python dictionary and set, the implementation is very closely match what we are going to talk about.